Okay, thanks. Okay, so this presentation is going to be on an immensely important topic that's not talked about a lot, and it turns out to be very tricky for RDMA. It's part of the ongoing work that we're developing in the OFV working group, and the implementation, part of the infrastructure is there, and we still have more to do. So what are resets? So many times you have occasions that are unexpected that you need to asynchronously either restart or disable a device. For example, you could have device errors, or just even the device is not functioning. In other cases, you might want to do something administratively. This could be, for example, an administrator unloading the device driver for like some software upgrade, or an unplug event, like when you're migrating a VM and you have SRIOV in place and you want to detach the hardware. In all these cases, you have to stop the hardware. You have to bring it to an idle state, a known state, and then you need to stop traffic. And one example for this is the TX timeout function for Ethernet NICs, right? Whenever the operating system senses that it didn't get any completions for sense, that they're lagging too much, something must be wrong with the NIC, please restart yourself. And then it could continue, hopefully without all other consumers of this service knowing about it. So let's look a little bit about what resets entail. So first of all, we want to be able to reset the device without any dependencies on the consumers of the device. For example, we don't want to have a situation where the device itself needs to stop, and then we have some consumer say, hey, please let me send this packet first. But I want to stop, but I want to send this packet. I mean, we have to break this loop and reset the device and then continue traffic afterwards. We want to do it in a very timely manner, because usually resets are detected by timeouts. We want to minimize the effects on consumers of the technology. And finally, if something bad occurs, we want to keep the device disabled. Now let's look a little bit at why this is challenging for RDMA. Well, first of all, in RDMA, the device is stateful. All its transport resources like QPs, the completion queues, shared receive queues, all these objects are directly manipulated by ULPs and applications. And when you reset the device, all the state that was held in hardware is now just like goes away. So it's hard to make it transparent to applications. The other main point is about Userspace. So Userspace hold direct references to these hardware objects, and Userspace is not trusted to cooperate when resets need to occur. And this is an important subject that we need to tackle. Finally, we have pretty complex dependencies with RDMA. Instead of usually the stack where you have a driver that plugs into a subsystem, and then from there upwards it's all software. With RDMA, there could be direct references to the hardware at upper layers of the stack. And let's say there are weird or subtle things that can occur due to these dependencies. So for example, let's look at the ICER ULP that has a QP, which is a hardware resource. And in turn, ICER uses CMA, it uses CN that uses the MAD layer, which also has a QP, which is a hardware resource. And let's say that something is malfunctioning, and we need to reset this chain. So ISR depends on MADs, so we should probably tear down ISR first. But then if ISR did some connection attempt and the MAD layer, nobody spoke to it yet, and it tries to send this message and it doesn't get any completion, then everything is stuck. So what do we do here? So in order to tackle these kinds of dependencies and keep stuff simple, because all these kinds of flows, of reset flows, in principle, they're asynchronous, and asynchronous is hard. We don't want to introduce a new case, so we want to stick with the remove and add flows, which already take care of proper dependency order. But the thing to notice is that the remove is not a standard remove. It's an abortive remove, because the device is not functional or is inaccessible. For example, on power systems, if you have a PCI error, the slot is isolated and the driver doesn't have any access to the device at all. Okay, so in terms of this abortive shutdown, let's see what I mean by that. So the path that we found is, first of all, to put the device in some state that we call error mode. And I'll talk a little bit about what that means. And after that, we set up the fatal event, which basically goes through all the layers of the stack and notifies everybody that something is bad. So the device is not going to function properly. And after that, we can unregister the device, which basically calls the standard remove sequence, which goes right to the upper layer and then kind of folds everything down back to the InfiniBand core. So what is this error mode that we want to do? First of all, it means that for all the in-flight work requests, we want to complete them in error, and we want to complete new ones in error, or alternatively, prevent new work requests from being posted. That's one thing. Another thing that we want to do is to be able to successfully close resources. Now, this is a very subtle point, but it's a very important one. Consider that you have a device that's not reachable and you want to close a QP. So what are the options? One option is never to return the call. I mean, that's not good. I mean, basically it means that we're stuck. The other option is to say, hey, I failed to close the QP because I can't access the device. And let's think of what a ULP is supposed to do with that. If it says, hey, I'm trying to close a QP and it failed, okay, I'll print something to the system log and I'll continue. This might be okay if the device is indeed reset, but in the normal case that something else like a dependency occurred, for example, you might be trying to close a completion queue, but you still have QPs referencing it. I mean, these are standard errors. You can't just close or think you're closing a hard resource and free the underlying buffers and memory while the device might still be accessing it. You just can't. Because otherwise, in the normal case, you're facing memory corruption. So essentially what we want to do is we want to have these verb calls that close resources to succeed, so ULPs will always do the right thing. And for other system calls, we can just fail them. I mean, if you're trying to open a new resource or modify it, that's okay, we can return an error. So now that we have this device error definition in place, we can see how these ULPs can close and fall back even when the device is inaccessible. Because any new work that they're going to do is going to fail, but they will successfully close the resources in a secure way and allow the device to be reset and then recreated. Okay, So let's look a little bit about the assumptions that we have on the ULP somewhere in the chain when it receives this device fatal error. So the first thing is that it can assume that the device is in error state, as defined in the previous slide. And once it assumes that, it knows that it can close resources if it wants to, or it can wait to when it receives the remove call. But most importantly, it has to continue to process incoming requests from any ULP that is above it, even if it knows that anything that it tries to accomplish in hardware might fail. So, for example, let's say that you have some incoming call that requires you to, I don't know, establish a new attachment to a multicast group. You can't condition that operation to succeed. You can't condition the incoming call on the success of these kinds of operations because the device is in error. And if you don't return these calls, if you block, you're going to basically you're going to cause this flow to deadlock. So all these API calls from upper layers have to succeed, even if the hardware is not functioning. And if you do that yourself, then you don't need to make any other assumptions on ULPs at lower levels. And of course, when you receive the eventual remove call, then you just release the resources. Now, there could be additional optimizations to what a ULP can do. For example, if it receives the fatal, it can just return immediate errors to these calls without trying to invoke verbs and discover that. That's one thing. The other thing is that it can avoid any kind of internal reset flows. For example, if the MAD layer gets completions and error, I think it tries to reopen the QP. I mean, just get a fail event. Why bother? I mean, it's going to fail again and again. So it can, these kind of flows can be optimized, although it's not a great waste. The device is going to go down very shortly anyway. But these are the stuff that you can do. Okay, when we come to Userspace, the problem gets more complex because Userspace is holding references to the device. Now, this might be okay for a software-only subsystem, like a file system, that you prevent the file system from being unloaded from the kernel as long as you have applications with open file handles on that file system. But in case of RDMA, we're just talking about a hardware device that due to some PCI error I need to reset, or due to a hot plug, I need to do something. I can't let the applications do that. So if I look at some of the solutions here, so the first solution, so-called solution of let the application hold the kernel hostage, is not a real solution for devices. Hey, let's just force the application to release the resources. And yeah, sure. I mean, no way of doing that. And we have the easy way. Let's just kill the application. That's going to release everything. Again, we don't want to do that. Maybe it's a huge application that it uses an RDMA device, and it could fall back to TCP over some Ethernet NIC if it needs to. We don't want to do that. So what we found as a way to overcome that is what we call to zombify devices. So what does that mean? A zombie RDMA device is a device in error mode as defined a while ago, but completely implemented in software. It doesn't hold any reference to the hardware, and of course when the last reference to the zombie is released, then the zombie is going to be destroyed. Pretty much like dead processes. So these two zombies are actually implemented by the IBU verbs layer, and we'll see also part of it is in the UCMA, but the actual device itself is free to reset, unregister, and re-register. These devices used to be hardware devices, but they become software-only representations of what they were. And once the last reference is gone, they're just going to go away, and the applications can reopen the same device with the same name, by the way, and then continue to operate. So that's the idea. Okay, so let's talk a little bit about how zombies come to the world. The first place that they arise is in uverbs. Basically, when the RDMA core layer unregisters device, what we do in uverbs is we disassociate the uverb context from all hardware sources. We just go through the IDR trees and call into the vendor, release all of the objects in the proper order, right? QPs, CQs, memory regions, everything, and close the resources and hardware. The next thing we do, we call into the provider and give it a first chance to disassociate any kind of resources or memory mappings that are only internal to the provider, because providers have relations between their user space and kernel space drivers that need to be shut down cleanly, and this is not something that's managed by the IB framework. So for example, if we have doorbell regions that used to be mapped to the PCI bars, we can now redirect them to some 0 page in the kernel. We can also remap them to some page that leaves some information or some traces for the user space driver to pick up. Of course, we still can't allow any kind of synchronization or at least not trust our user space driver to cooperate, but we give the provider the best effort to make this happen. But the point is that after disassociate context returns, we know that we can completely return from the remove one call, and then the hardware can be reset, can be removed. You can unload the driver at all, and the user space still has the reference, still has this uverbs file open. From that point on, any kind of verbs system call that that's being called into uverbs just returns EIO. And it's up to, from now on, it's up to the user space driver to emulate this device and error model to the application itself. That's one place. The other place where we need to invest is UCMA. Here we have a problem where applications hold RDMA IDs that reference devices. It's the same problem. So what we do here is we actually close the RDMA IDs in the kernel while still leaving the UCMA file objects in place. And the behavior is similar. You can't do anything with an RDMA ID other than close it. We do ensure, though, that all the UCMA events that pertain to this RDMA ID are enqueued, especially the device removal event. But again, UCMA now allows the device to be disassociated while still having active UCMA files that are referenced by user space. Now, it turns out that there's nothing needed to be done in UMAD or UCM because these don't directly hold references. These pass complete payloads and then they're dispatched by lower layers that interact with hardware. There's no indirect interaction to hardware with UMAD and UCM. So in summary, let's look at what the provider needs to do to support the reset framework. In the kernel, it needs to implement this notion of an error mode. It needs to implement the disassociate uContext entry point. As I said, for some devices, they might need to remap the bar. For other devices, it could be a NOP. Depends on the implementation. Probably for software RDMA device, it's going to be easier. In any case, it's the provider's choice what to do in this callback. In terms of user space, you just need to, again, implement this error mode abstraction. In terms of status, the core reset support was added to uverbs and UCMA in Linux 4.3. And also we accompanied that with the first use case with ConnectX 3 devices. In Linux 4.4 we added ConnectX 4 kernel support for PCI resets. And right now we're working on completing the connectix for kernel flows. We still have a long way to go with this. The first thing is in new verbs, maybe talk about the grace period. So let's say that something occurs like not because of like a PCI error, but just because the super user wants to unload the driver. So maybe we have some important daemon that would like a chance to at least gracefully close or send final goodbye message before being completely shut down asynchronously by the kernel. So maybe allow it, a second or two, and only then zombify the device. In RDMA CM currently doesn't support this flow. It opens all the devices upfront when you load the process. When RDMA CM initializes itself, it opens the handles and it never refreshes them. So right now, RDMA CM, if you incur a device in reset, I think that you're stuck with a dead handle. So we need to add work to RDMA CM to accept the event of a fatal event and refresh its device list whenever it receives such an event, and probably also from time to time detect if new devices have been added to the system. This is also something that's not handled with RDMA CM. Another nice idea is, let's see if we can maintain the context when the errors are transient. One example of that is, again, the TX timeout handler with Ethernet devices. So when you have some problem, you just reset your NIC. You don't lose your VLAN child devices or the IP configuration or anything that was any soft state that was associated with a device. You try to transparently reset the hardware, and when everything is done, you just continue from there. And currently, as I said earlier, the reset flows basically unregisters an InfiniBand device or RDMA device and then registers it again, which means that the ULPs also destroy their instances. So why can't we have the same for IP over IB? Why can't we have an SRP device that if the hardware goes away, instead of just this SCSI SRP device doesn't need to disappear. It can maintain its state and then try to reconnect after the device is reinitialized. No need for administrative intervention to establish that. I mean, right now that's what you need to do. I mean, you can use a script and then you just play the same state and into the kernel. But what we want to achieve is to be able to do that transparently. So the idea is basically in the IB client introduce two new entry points, which I call here stop and start. They're like add and remove, except that the IB device handle itself remains. So when you receive the stop call, what you would do, you would close all hardware resources just as in remove calls, but you would not free your context. And later on, when you get start, you just recreate the hardware resources and then according to the state that you already have. So the RDMA device handle doesn't go away. The association stays there. Nothing happens to the context. The only thing that you need to make sure is that you close all the hardware resources, and when you reopen them, you can't make assumptions about their IDs. I mean, you might get another QP number when you reopen the state. But other than that, this is a way how to maintain the context. The final point is persistent naming. So we have UDEV rules for Ethernet devices. It might be nice to have similar stuff for RDMA devices, like having IB0 being persistent according to the node GUID, even if devices are rescanned or added. So currently, you could always in Userspace, you can do the same if you look up the node GUID yourself. I mean, like after reset, It could shift from IB0 to some other higher number. But we might want to add kernel support for changing the names, and then have UDev take care of that. And yeah, I think with this, I'm done. Questions, please.
So, Liran, I think this is more of the entire device failure. I mean, this case of RDMA reset you explained is specifically more of the whole IB device is getting, it entered into the fail mode or something odd happened. I was thinking of another case which is a very small and sub case of this is on an IB device if you have a bunch of RC connections and let's say you happen to get into trouble on one of the connection being used for RDMA and you want to just cancel that particular connection or resurrect that connection because and I think the reasoning you mentioned, a lot of them apply for that individual connection as well. The current thought process we were thinking of doing that is again the similar thing, put that queue pair connection into the error state, flush all the in-flight work request and all of that, and then do a RDMA, CMA reconnect or whatever, recreate that connection. Is that best we can do, or there is something better you can suggest, or anyone has any suggestion on that?
Okay, so I think that we need to make a distinction between resetting a complete device that malfunctions rather than having nice features or reconnect or bonding or stuff in terms of connections. Because a failed connection is not a failed device. I mean, a connection could fail because misconfiguration, the network, because, timeouts, because of congestion. The device itself is not failing when you have a failed connection. So we can talk about new services in the RDMA CM, for example, automatic path migration support and migrate back to the primary path when it's done. We can have something like inherent multi-rail support and maybe add middleware to handle that. So I think that's the place to handle the sort of stuff that you're talking about. It should be some layer that offers shared enhanced connection services as part of the stack. But I wouldn't tie it to underlying device resets that I presented here.
That's how I started. I know this is the separate problem what I was trying to describe. It's not a catastrophic device failure, but it's more of... So some of the ULPs and me and Chuck were talking about it, that for example NFSO or RDMA and RDS is where we would like to have this functionality, and APM is definitely one part which basically seamlessly will handle it. But let's say even in an absence of APM, the process which I explained, does that make sense? Like the error state and just recreating the new connection.
I think that we'll need to talk
okay.
after the session about specific solutions.
Sure, sounds good.
Okay, so I had a quick question. So does this require any changes in the provider, IB Works provider, and if that introduces any branches in the critical paths, like especially when on the send path where you have to check whether I'm a zombie or I'm not a zombie, or locking,
Well, I think it mainly depends on the provider. I mean, one example for that is completing work requests in error. Essentially, if you look up the specs, it turns out that applications shouldn't make assumptions on work requests completing at all when the device is in error. I don't know even in a single application that does that, and I think the IB core itself doesn't handle that in the man layer. Because usually what people do is they actually put context in the work request ID, like a pointer, and they don't hold a shadow of the objects that they need to release. They rely on that work request ID being returned in completions. We decided to handle that. Basically, we have a software backup to ensure that these completions are occurring. If you have a software provider, probably you don't need to worry about that. You can do it in a more straightforward manner. And again, it's very provider specific. So we have an infrastructure now in place, and as I said, for some providers, this disassociate context is going to be a very trivial operation.
I have one question, or clarification. So is the real issue here that all this state is like on the adapter, and if you like reset it, it just gets lost to the world? And that's why you would have to like tear down all these connections and reestablish them in the ULPs?
I mean, we could have stuff much more complex, like trying to read the last known state and try to feed it back. But again, I don't think that, at least spec-wise, you can't. There's some state that you can't obtain right now, and it's also very complicated.
But isn't it just because of the way that you've implemented RDMA in the hardware, as opposed to like Omnipath that implemented all this state in an onloaded driver, where there's very little state on the adapter?
I think for a software implementation, it's going to be easier because the context is in software.
Okay.
But then you don't get the performance.
Well, I disagree. Will you get the performance?
Yeah, so to the question about, like, you mentioned that the MAD stack has this problem where it expects a completion back. And we've actually run into that problem specifically because I've worked on the MAD stack, so I totally understand that. So what do you think about changing those semantics, especially for things like UDQ pairs, so the ULPs don't have to worry about that?
That's exactly what we're doing. When we have a device error, we ensure that you get the completions.
Okay, so are you advocating some sort of layer where ULPs don't have to worry about this? Or are they going to have to deal with all their Q-pair state? Because I kind of thought that's what you were saying.
I think that I'm advocating a case where we define the semantics of a device in error, and given the definition that I've put here, I think ULPs will have less worries.
Okay, I think there's a little better way to do it, but that's okay.
Okay.
Yeah. All right.
Let's talk.
We'll talk.
Yeah.
Two questions. With respect to the zombie mode, and you're in SROV mode, is each VF can be totally independent and be in zombie versus, or is it,
Okay. Well, the notion of a zombie is it's a software notion, and it occurs in each instance of the operating system, right? So if you have like a bunch of VMs with SRIOV, then now zombies occur when the VF is inaccessible, as seen by the virtual machine operating system. It's not related to what occurs in other VFs or in the PF in the hypervisor.
right? Okay, good. And the other clarification I had with start and stop. So is that only used when, I mean, the upper level ULP doesn't know that the device is in zombie at this point, right? So is that like parrot mode, not quite dead yet? Or what?
Okay, so my thoughts about the start-stop thing is that we need to define a new flow in the IB core, which means that I want to attempt a recovery. So what we're going to do in the recovery is send a fail event, send a stop, then send a start. And ULPs that won't implement the start-stop, they'll just get the standard add remove. So they'll lose their state. So we can gradually add support. There are some ULPs that could easily adjust to that. For example, IP over IB, it already has like interface up-down, so it knows how to close its resources. Essentially these are the same flows, except the final stage of releasing your context, that's the only thing that you avoid. So I don't expect like new asynchronous flows in ULPs to support this. I hope it's going to be pretty straightforward.
Okay, thanks.
Okay, thank you.